In this video I'm looking at the second question and the end of unit test from DC Circuitry. So what we've got here is an EMF source with negligible internal resistance, and it's connected to two lamps which are in parallel as shown here. The first thing you need to do is work out the current going through the battery. So using Kirchhoff's current laws, if we want to know the current going through the battery, that's going to be our total current here, and that's going to be formed from the current going through P and the current going through Q. So essentially what we want to do to get I total is it's going to be the current going through P plus the current going through Q. So let's do some calculations. So we know that P equals IV. This is one of your equations, so I going through P is going to be the power of P divided by the potential difference across P. So the power of P is 36, because it tells you it's 36 watts. The potential difference is 12. So you've got 3.0 amps going through P. If we do the same sort of thing, we want to do current going through Q. It's going to be the power of Q, which was 6, divided by the potential difference, which was 12, gives you 0.5 amps here. So the current going through the battery would be the summation of those two, which would be 3.5 amps for this question here, giving it to the right numbers, significant figures there. So that's your current going through the battery. So we want to calculate the resistance of P this time. So we can use one of two equations, or we could use P equals I squared R. Either of them work. So by doing this, the resistance is going to be V squared divided by P, and we want it for Q, so it's going to be this one squared, so 144 divided by the power, which was 36. So you're going to get 4.0 ohms as the resistance here. Scrolling down, doing exactly the same thing for Q here. So let's do it using the other method this time, so you see both. So the resistance, it's going to be the power divided by I squared. The I in this case was at 0.5, so that's going to end up with 0.5 squared, which is 0.25, so it's a quarter. Power was 6 watts, 6 times 4, or I guess 6 divided by 0.25, or 6 times 4, which gives you 24 ohms in this case, which is your resistance of that. So you've seen both methods we could go about doing that for this equation here. So next thing it asks you is state and explain. So state is just say what would happen, and explain means use equations to show what's going on. What the effect of the brightness of the lamps in the circuit would be if it had significant internal resistance. So I always like to explain these questions using potential divider equations. So what we need to be thinking about, or in this case actually you could use your EMF equation as well. So the EMF equation states that the EMF is equal to the sum of the terminal potential difference, which is this V here, and the potential difference across the internal resistance. So the potential difference that's available to the circuit is going to be the EMF minus the potential difference across your internal resistance. Now, as you increase the internal resistance, make it non-negligible, this is constant here. So what's going to happen is if you increase this little internal resistance here, what you're going to do is cause the terminal potential difference to decrease. So essentially what's going to happen is instead of applying 12 volts across the two different bulbs, you're going to apply less than 12 volts in this case. But the important thing is to then link this to the actual brightness. So you also know the brightness of a bulb is calculated by power, which is this, V squared over R. The resistance of it hasn't changed. This term here has got smaller here, which must mean the power has got smaller as well. Lower power means lower brightness. So state what's going to happen, the brightness is going to decrease, and explaining it, you first explain this, that the terminal potential difference got smaller, and then linking that to power, explaining how resistance is constant, this goes down, therefore the power is going to go down. Now equally, you could think about it in terms of current. So increasing the internal resistance increases the total circuit resistance. If you increase the resistance for the same EMF, you're going to decrease the current, and then use P equals I squared R to explain that if the resistance is the same but current is reduced, power is going to be reduced, so brightness is going to be reduced. And that would be yet another perfectly reasonable way of explaining it, but this is my preferred method in this case, using Kirchhoff's series voltage law effectively here. Okay, so this next question is actually asking you, well, what if we connect them in series instead? So the 12 volts no longer applied across them in parallel, but we've connected them up in series. So the first thing to remember is that using Kirchhoff's series voltage law, that the potential difference is now going to be shared across P and Q. So if we look, we call this one VP, we call this one VQ, then VQ plus VP must be equal to 12 volts. That's what Kirchhoff's series voltage law tells you. So now we know that, we need to think about how that's going to affect the power, because that's what's going to end up deciding how bright they are. So remembering we've got this equation here, V squared over R. So essentially, for the bulb P, R is unchanged, so this here is a constant. But we know the potential difference has now decreased because it's now being shared, which must mean the power is going to be shared. So essentially, for both of the bulbs, they're going to end up dimmer than before, and they're going to because they have a reduced power dissipated by that bulb due to the smaller potential difference across them. So then, looking at the next question, state and explain which of the lamps would be brighter, assuming the resistance of the lamps doesn't change with temperature. So brightness is all about this equation here. And then likewise for Q. Now, the key thing to remember here is that because they're in series, the current is the same going through P as it is going through Q. So these two terms here are the same. So what you find is that in this case, the power, and therefore the brightness, is just directly proportional to the resistance. Now we calculated in the previous question that RQ is much bigger than RP. I think this was 24 and this was 4. So this term here is actually 6 times bigger than this, so Q is going to be considerably brighter due to the increased resistance. And it's using this equation that allows you to explain why, because the power dissipated is directly proportional to R, and the resistance of Q is considerably greater than that of